Okay. There it goes. Okay. Apparently, you got to mess with the camera to get it to focus. Okay. So we know that the target pH is 5. And so now we can go ahead and start looking at how we do this calculation. So target pH is 5. We got the volume of buffer we want is 500 milliliters.
Yep.
We know that the total concentration is 0.2 molarity.
Yeah.
So if we wanted to do part A, where part A is you get access. So you notice in the problem you have access to 3 different things that are going to be useful. After we realize that we have a target pH of 5, we can say, okay, the only things that are going to be useful are acetic acid, the acetate anion, and base, and strong base. Right? So we can make our buffer just by mixing the correct amounts of acetic acid and acetate anion, right? Because that's what defines a buffer, is having the weak acid with the conjugate base. So if we have the right amount of those 2 materials, that could make a buffer. That's what part A is asking us to do. So if we look at this, we can say we can just do Henderson-Hasselbalch for this. We can do pH equals pKa plus log conjugate base over weak acid. Square brackets. Right? So we can say 5 equals 4.74 plus log conjugate base over weak acid. Right? We can solve for the ratio of conjugate base to weak acid. And then we can also use the fact that we know 0.2 molarity is equal to the concentration of conjugate base plus the concentration of weak acid. And we can essentially do 2 equations, 2 unknowns. Now, I want to do a warning, because I had a couple students in office hours last week doing the buffer calculations, and we set it up like this. There's an easy way to do the algebra, and there's a hard way to do the algebra. Both of them eventually get you the same answer. Both of them are fine to do it, but one will take more time and one will take less time. So if you take this and you subtract over weak acid, then you plug in 0.2 minus weak acid into here, that works. But it's actually a little bit algebraically easier if you take this and you turn it into a fraction and then solve and then substitute into the other one. Just makes the algebra a little bit easier. So do me a favor, get your calculators out. 0.5 minus 4.74 to the power of 10. I need a couple people to agree with that. So our ratio of conjugate base to weak acid is 1.8. The easiest substitution is to say 1.8 weak acid equals the concentration of conjugate base and plug this thing into here. That's going to be easier algebra. Now, the algebras, the answer will be the same eventually, right? It's just a matter of which one has easier algebra. For me, it's easier to have 0.2 equals, let's say, 1.8 weak acid plus weak acid. That's easier for me than having a plus something in the logarithm. So I like doing it this way, easier. You add those 2 numbers together, you get 1.8 plus 1. That's just going to give you 2.8 weak acid equals 0.2. This allows me to solve for my concentration of weak acid. I can't do that in my head. 0.62? 0.072?
Yeah.
Oh, yeah, that makes sense. I did 2 divided by 3, so of course I was off by a decimal point, and I went smaller instead of bigger. So that's our weak acid concentration. We can then take this weak acid concentration, plug it into here to get our conjugate base concentration. I'm going to go with 128. I'm gonna keep those extra decimal places. 0.128. So that gives me the molarity of the weak acid and the conjugate base that I want to have. Great. I can then take those concentrations of the weak acid and the conjugate base. Let's see, you can't quite see those anymore. Oh well, they're gone. So we're going to take the concentrations of the weak acid and the concentration of the conjugate base. Weak acid is equal to 0.072 moles per liter. And we know that we have, or we desire, we want to get to 0.5 liters because that is going to be the 500 milliliters. So if we looked at that, getting my framing better. That'll be better. So I know my concentration of weak acid is going to be equal to 0.072 from the Henderson-Hasselbalch equation, moles per liter. Remember, this is weak acid at equilibrium. This is not at the start. This is not at the initial point, but the initial point and equilibrium point are the same. This is the weak acid concentration at equilibrium. If I take that 0.072, multiply by the total volume we desire in our buffer of 0.5 liters, we will get the moles of weak acid that we want to have. 0.036. 0036? No, 0.036. No. 0.036. 0.072 divided by 2, right? Because 0.5 is 1/2. And this will be moles weak acid at equilibrium. We can do the same thing for our conjugate base, which is 0.128 molarity. We can multiply by 0.5 liters, and that will give us 0.064. Weak acid at equilibrium, conjugate base at equilibrium. So, if we have access to both acetic acid and acetate anion, just put the moles of that into our solution, fill up the rest with water, you're done, right? So part A pretty much says, get these numbers, mix that amount of each one in, and you're good, right? Because that's one way we could make the buffer. If I have weak acid and I also have the anion of the weak acid, the conjugate base, you put those things into a beaker, that makes a buffer. You don't need to do a titration. Almost every time we've done this in class, we've done it via titration. So we've done the way that part B does it, where it says, okay, now do it where you're using a pure material and a strong titrant.
So they wanted it says for us to calculate the grams and the milliliters if it's liquid. So
yeah.
Since the conjugate base is in the form of a solid, would you just multiply with molar mass?
Yeah. So since the problem does ask for the grams and volume, you just take your moles, multiply by your molar mass, that gives you the grams. Take your moles, divide by your molarity, that gives you your volume, right? That's 127 stuff. That's easy. Okay, should we do part B? So part B is essentially going to be the part that's identical to what we did in lab, where we're going to do this via titration. And so we just have to do a little bit of a logical change, right? We have to do a couple stoichiometric considerations. that I'm going to go through relatively quickly because hopefully they're familiar at this point. Thing number one. The moles of strong base needed is equal to the moles of conjugate base at equilibrium. So the moles of strong base needed, I should put at start. The moles of strong base that we start with is going to be equal to the moles of conjugate base we have at equilibrium. That's the stoichiometry. Is that okay? Thing number two. The moles of weak acid at start is equal to the moles of weak acid at equilibrium plus the moles of conjugate base at equilibrium. Is that one okay as well? And there's there's two easy arguments we could make for this. And notice, this means I already have the moles of strong base I need. It's 0.064 moles of strong base. And to get the moles of weak acid I want, I just have to add these two numbers together. We've all done that problem hopefully like a dozen times at this point in the quarter. Question?
So for example, in midterm 2, you asked us to list the assumptions that we made. Would these be ones that would count?
Not exactly. So midterm 2, at some point I asked for the assumptions that you needed. These are not really assumptions. These are like just results of stoichiometry, right? We could write down the reaction. We could see this happen. Most of the assumptions come in with the Henderson-Hasselbalch equation, right? Because when we do the equilibrium, we're using the X is small approximation. We're using the fact that water is negligible. And, well, the one on the midterm was a polyprotic, if I remember correctly. So you also had to assume that Ka1 and Ka2 were far away from each other. In order to put a little bit more substance with this stoichiometric consideration, let's go ahead and the way that I think is easiest to think about it is to just look at the titration curve. And I find the titration curve to always be a good thing to draw to kind of think about what's going on. So when we think about the titration curve, for part B, we're essentially starting at this point on the titration curve. We're making a buffer through titration. So how much of my material, what percentage of my material is weak acid at the start? All of it. What percentage of my material is weak acid at the correct point? Well, whatever value we solve for. But all of the conjugate base comes from the weak acid that we start with. Right? Stoichiometrically speaking, what we have is HA plus OH minus goes to A minus plus H2O. That almost looks like an A. Right? All of the material I start with here, if I start with, if I can do math in my head, if I start with 0.1 moles here, I'm going to subtract off whatever moles of hydroxide I start with. If I do 0.036 based off, whoop, not 0.036, sorry, 0.064 based off of the calculation we did earlier. The 0.064 is clearly my camera. Focus. There we go. Okay. The 0.064. The 0.064 is clearly the limiting reactant. I just can't move too fast. It freaks it out. Okay. Oh. The 0.064 is clearly the limiting reactant. I think it's like seeing behind the board. Yeah, it's seeing behind the board and focusing on the wrong thing. The 0.064 is clearly the limiting reactant, so I'm going to minus 0.064, minus 0.064, plus 0.064. I'm going to have 0.1 minus 0.064. That gives me my 0.036 left over. 0.0 and 0.064. Notice all of it started as HA and becomes the conjugate base weak acid. Now, you don't actually have to do this stoichiometry step. If you have your stoichiometry considerations, which are not technically approximations, they were just tricks that we realized, oh, the stoichiometry always comes out the same way. We can always do this in the stoichiometry. That's how you make a buffer. Question?
We kind of went over 3 assumptions. I think there were a total of 5. Could we go over the last 2?
Oh, on the midterm?
Just kind of overall, they were like
Oh, there were only 3 assumptions, and then there were 2 tricks from the assumptions.
Okay.
Right, and let's see if I can remember all of those. So the tricks that we use, first thing we do is the X is small approximation. If we wanted to put it in the wordy way that we do when we're looking at our weak acids, or is the disassociation of a weak acid is, how do you spell negligible again? I put an E on the end too. Negligible. And I think the E gets an accent and you put an umlaut over the first one. Negligible, right? The disassociation of a weak acid is negligible. We just call that the X is small approximation. We also have the approximation we also say the water equilibrium is not significant. You could also say negligible, but I didn't want to try to spell it again. So the water equilibrium is not significant. Water is not contributing a lot of H plus or OH minus to our reaction. We almost always assume that. That's a very common assumption. Then we had kind of some stoichiometry tricks that we could use, which I'll number differently, because I think people did think they were assumptions, but they were just tricks. Trick number, the first trick was that if you have a ratio of concentrations, then you can just convert it to the moles when the total volume of each solution is the same. Since our titrations were always in 1 beaker, that was always true. That always worked out. So we were always able to do this trick, and just, we could have just jumped to moles here. We would have had to do, if you did 0.2 times 0.5, you would have been solving everything in terms of moles, and that would have been fine. The other 2 are these guys. The moles of strong base at start equal to the moles conjugate base at equilibrium. Oops, I did number 3 twice. That's 4, and then 5 was moles of weak acid at start equals moles of weak acid at equilibrium plus moles conjugate base at equilibrium. Right, and both of those things really came from the stoichiometry that I just erased. They're not really assumptions, they were just tricks that made it so we didn't have to do the stoichiometry table over and over and over again when it was the same thing every time. However, that's also what got a lot of people in trouble on the second midterm, because on, I think it was part C, these assumptions didn't work because you weren't doing it via titration. These assumptions assume that these assumptions these things we're using, assume that you're starting with all weak acid and then adding strong base. On the midterm, you had some weak acid and some conjugate base already present, and you were reacting both of them. So these didn't work, and everyone just thought they did, and I took out points. Question?
Yeah. So when we did the titration part for the titration part of this problem, not the combining between acid. Couldn't you also use Henderson-Hasselbalch for that because of how the stoichiometry table is?
Yeah, so we could have used, with all of this in mind, we can use that kind of shortcutty Henderson-Hasselbalch equation that got everyone in trouble on the second midterm, where we can just plug our stoichiometry into our Henderson-Hasselbalch, pH equals pKa plus log molarity of strong base volume. You talking about this one?
Yeah.
Molarity weak acid, volume weak acid minus molarity of strong base, volume strong base. That is the stoichiometry. That comes from these ideas, right? The moles of strong base at the start is the moles of conjugate base at equilibrium, because that should be moles of conjugate base at equilibrium there. But we've got moles of strong base at the start, same thing, because of this stoichiometric trick. The reason it didn't work on the midterm was because there's always a 0 plus there, right? And we usually ignore adding 0 to something usually doesn't matter. On the midterm, it wasn't a 0. There was some material there that you were supposed to be reacting. And everyone jumped to the shortcuts. And it made me think none of you understood the stoichiometry. Not none of you in the room, none of you in the class. And not none of you, but most of you. A question there, then there.
So what is the 0 in the stoichiometry reference sense?
So if we looked at our stoichiometry again, we've got our HA plus our OH minus goes to A minus plus H2O. We got our start, we got our 0.1, we've got our 0.064, if I remember correctly. I've got the number right up here, 0.064. And we had 0. Then we had minus, minus, plus, right? We have 0 plus whatever this number is. On the midterm, that wasn't 0. That had some numerical value associated with it. And since most students just regurgitated the shortcut, I wasn't sure if you were just regurgitating the shortcut, if you understood where the shortcut came from, if you understood the stoichiometry. There just wasn't a lot for me to kind of be like, oh, I see how you came up with that. You didn't even write down the stoichiometry, you general, not you specific, but you didn't even write down the stoichiometry to be like, oh, that's why you made that mistake. You just wrote down the equation from the notes, and I was like, no idea how much of this you actually understand. Question?
So on the second midterm, there was a question that was asking, why can we not use the Henderson-Hasselbalch at the equivalence point? And I'm still slightly confused.
Yeah. Let's look at, so again, with this same idea, why can we not use the Henderson-Hasselbalch at the equivalence point? Great question.
Is it because the pKa is, or the pH is like no longer within plus or minus?
Yeah, that's one way to say it. You can say, look, we only use the Henderson-Hasselbalch equation when we're in the buffer range. And if we're at the equivalence point, we are away from pKa plus or minus 1, so we can't use it. And that's a great kind of rules way to say, okay, we can't use it. We have this rule for when we can use it, when we can't. But what's the chemistry or the logic or the science behind why we can't? Because if you just said the rules say I can't, I'd be like, let's question the rules. Where did the rules come from? Do the rules make sense? Don't know.
Yeah.
So remember, when we're doing the Henderson-Hasselbalch equation, we're doing a shortcut for the equilibrium, right? We are doing HA plus H2O goes to A minus plus H3O plus. We're doing an ice table. We've got our concentrations. We've got like 0.036. We've got like 0.064. We've got 0. We've got minus X plus X plus X. We use the X is small approximation. We could do 0.036. We do 0.064. We do X. Now let's say we go to the equivalence point. At the equivalence point, 0.064, all of these numbers change slightly. 0.064 would become, let's go like to just close to the equivalence point, not quite there. Let's say we've got 0.099999, and our HA is 0.000. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 1. And we've got 0. I'm going to do minus X plus X plus X. What's going to be the problem with this?
It's gonna change, the conjugate base, like, it's gonna, X is gonna be.
Yeah, not for the conjugate base side, right? It's here, this small number minus X is probably going to be significant, right? Also, you could argue that the equilibrium would lie this way, and we should have a minus X plus X. But whatever the way you want to look at it, right, we could also look at this and say, actually, in this case, we should be looking at it as A minus plus H2O goes to HA plus OH minus. And in this case, I'm going to set up my ice table the opposite way with 0.099999 and 0.000001, 0. I'm going to do minus X plus X plus X. The equilibrium either way should get us the same answer. It's just a matter of how easy the calculation is to do. But either way we do this, X is small approximation fails, or the X is small approximation fails.
Is that because, like, the KA, I'm just slightly confused, like, why the X would, like, how you know that the X would be.
I'm estimating, right? Without a particular asset to look at, without other information. But one of the things to remember is that the Henderson-Hasselbalch equation has the X is small approximation inside of it, right? The reason that you can just jump to conjugate base divided by weak acid is it should be really conjugate base minus the dissociation, or plus the dissociation, divided by weak acid plus the dissociation, right? There should be this kind of change to it. And the Henderson-Hasselbalch equation automatically assumes the X is small approximation is good and eliminates that part. Once we get close to the equivalence point, there's a chance that this approximation is still good. There's also a good chance that it's bad. And you have to keep in mind, when we get to the equivalence point, we're actually not going to be like this. We're going to be at 0.1 and 0 plus X. And the question is X bigger than 0? Definitely. The Henderson-Hasselbalch equation would not catch that, right? It assumes that that X doesn't matter, because it assumes the X is small approximation works for both the conjugate base and the weak acid, and that would be a problem. That wouldn't work. So when we get to the equivalence point, the Henderson-Hasselbalch equation as a shortcut fails.
So it fails because it would assume that the acid will, like, not disassociate anymore, but the acid has to disassociate because it'll, like, essentially run out.
Yeah, more or less. We essentially have to assume that this association-disassociation is going to be significant. That is to say, the X is small approximation doesn't work. Question?
What's the difference between those two ice tables? You said they both work.
They both work. They both are going to run into different problems associated with them. This is going to be in terms of Ka, and you're going to be calculating a pH. This, you're going to get a Kb and a pOH. This one might not work very well. Again, because the X's small approximation is probably going to fail. So then you're actually going to have to solve the quadratic. In this case, if we've got 0 plus x, then we don't need to make the x a small approximation. But in this case, if we still had our 0.00001, the x a small approximation is probably also going to fail, and you're still going to have to solve your quadratic.
Right, okay. But are those two equations representing two different titrations?
No, these are the same. This is representing the equilibrium kind of going two different directions, right? The thing is, once you get your HA concentration close to 0, right, we should always, whenever we're looking at an equilibrium, we should almost always start with something that we haven't talked about since, I think, the second week of class, Q versus KEQ, to figure out which equilibrium is more likely to happen, Q versus KEQ, which one's actually going to happen. And Nicholas, can you put your water bottle away? Sorry, we can't have water bottles in this room. I know it's a hassle. Are we ready to move on to some other questions?
What was the third approximation? You said there were 3.
Oh, the third one only comes in when we're looking at polyprotics, that the Kas are very different from each other. I don't think I'm forgetting any approximations. Yeah.
Would you be okay doing part B on the long answer for the midterm? That was the one with the HNO3 and then
Yeah, we kind of just did a problem that was identical to that. So let me talk about something, because I'm completely willing to do it, but I also want to make sure that we're getting a good variety of problems in. And one of the things that's been a little bit problematic, midterm 2 and that buffer question really kind of clued me into this being a problem. That is to say, there are problems that are like parallel logic, right? I give you a problem where the wording and the concepts are not identical, but, well, the wording's not identical, the materials aren't identical, but the concepts and calculations are identical, right? The calculation and the concepts for the midterm 2 calculation are identical to the buffer lab calculation. They're identical to homework 4 problem 14. They're exactly the same. You do the exact same process. With that in mind, I'll go ahead and do it really quick. The amount of work I had to show to do this problem on my answer key was really small. What is your target pH? What's your target volume?
425.
What is your target concentration?
42.
Really almost the same as what we just did, right? We're going to have 10 equals 9.98, if I remember, 9.93, right? The pKa, I can't remember if it's 98 or 93. 98 or 93? 93 plus log conjugate base over weak acid. You're going to solve for that ratio. You're going to get something that's almost 50-50. I can't do it in my head, but you get some conjugate base over weak acid equals some value. It's almost going to be 1. It's going to be a little bit greater than 1. What value do you get?
1.175.
1.175. You also get 0.2 is equal to conjugate base plus weak acid. You substitute and solve. You do 0.2 is equal to 2.175 weak acid. You divide. That's going to be 0.0919 equals the concentration of weak acid. and then you're going to do that minus that. You're going to get 0.1081 equals the concentration of conjugate base. Am I good so far? Multiply by 0.425 to get your moles. Multiply by 0.4225 to get your moles. It's the exact same thing, right? For some reason, saying a polybasic compound just made all of you be like, I can't do it. Can't do it. Just made it so everyone kind of stopped. When really it's the exact same calculation. I've got to answer another question real quick. Do me a favor, talk amongst yourselves, come up with the next like 3 questions you want me to do. Talk to each other. Decide what the most important problems are.
So on part 8, number 5, like different.
Yeah.
Okay. First part what? Oh no, yeah, I think this is the case, like plural. I was gonna ask him, I figured it was just this one, like when will beta constantly be favored, when will there not? Oh, beta positives favored where there's too many protons. Beta positives favored where there's too many neutrons. I don't know why. Because I know alpha is when the like proton number or like mass.
Okay. Okay, so what problems did we come up with to work on?
So I have not a particular problem. I was wondering if we could take a review of indicators and how those might be used in a question or
Indicators? Okay, we can talk indicators. What else do we want to talk about? Yeah.
Can you use a midterm 1 titration problem?
Who's the titration problem on midterm 1?
Yes.
Like a multiple choice question, or?
No, like this. Wait. Is this titration?
I don't think that's titration.
Just kidding, it's not titration, but the free response question.
Midterm 1 free response. Okay, we can look at midterm 1 free response. What else do we want to look at?
Just a little bit of a review on
Okay, so indicators, midterm 1 free response, and homework 7, I'll look at a couple problems from there. Indicators. Indicators indicate. They indicate through color change. So when we look at an indicator, we can kind of generically write down our indicator chemical reaction as HIND. This is my protonated version of the indicator. Goes to IND minus plus H3O plus. This is my indicator acting like a weak acid. The other way we can write this is we can write down our indicator reacting with hydroxide to produce H2O. Either one is acceptable. I like this one a little bit better because this kind of gives us an idea of as I add hydroxide, I remove protons and I change colors. The most common indicator that we're probably, the indicator that we're most familiar with is going to be phenolphthalein, which is clear in its protonated form, and it's pink in its deprotonated form, right? So when we look at this, we can actually draw a titration curve for our indicator, and we can make note. I'm going to do it in red because I don't have a pink pen. We can make note that essentially we get to this point where I don't even like it like that. So we get to this point where as soon as we start to titrate, we get like a faint amount of color, and that color just gets more and more intense until we get all the way over here, right? So as we go through the buffer region, we pick up more and more color as we get more and more of our deprotonated form. This gives us the idea that an indicator changes color what I call PKIND. It's the indicator's midpoint, right? The indicator's midpoint is where you're going to change colors. If we were looking at one of our other indicators like bromocresol green or bromothymol blue, you switch from a yellow color to a blue color. So you would essentially get through this whole area, you'd get a green color with everything yellow versus everything blue. And that's another color change indicator we could look at. So when we look at this, we say, okay, I want my indicator to be at the point of its greatest color change. That's going to be like right in the middle. For phthalate, we actually like to go for the faintest pink. We go for this edge. But if we're looking at another indicator, if we wanted to look at bromocresol green, which goes from yellow to blue, your curve would look a little bit different. Your curve would essentially, I'm making it large for a dramatic effect. You'd be all blue over here. You'd be all yellow over here. I don't have a yellow marker. And you'd be varying colors of green through the buffer range, right? So the place that is going to be most useful is kind of right there where it's the most green, the midpoint of the indicator. Question, and then question.
Okay, so in the equation that you wrote for the indicator change up there, there's hydroxide. So
this would be for the reaction step, right? So after the reaction, you'd write down an equilibrium. The equilibrium would be the first equation I wrote down.
Okay, so you're not adding in hydroxide or anything like that? Are you titrating to base? Because you're adding hydroxide.
Yeah, so this is, keep in mind whenever, okay, another thing to be careful about, right? So this is the reaction step. And then you'd also have your equilibrium step. That would be the HIND to H3O plus IND minus. And how much this equilibrium step happens depends on the reaction step. Now, we could look at an indicator titration by itself, but we almost always have it in conjunction with some other weak acid that we're interested in, right? We never really just do a titration of an indicator and see the titration of an indicator. So we essentially are using our H3O plus equilibrium here to control the indicator, right? So we do this kind of like indirect thing with indicators typically. This means that we essentially pick the pH of interest from the system of interest, right? So usually we're looking at like a weak acid titration. We say, oh, we want to do a weak acid titration. We're interested in the midpoint of our weak acid titration. So there's a particular pH we want. And then we're going to pick an indicator that has a pH close to that interest. Or actually, you know what's more likely? More likely, we want the equivalence point of a weak acid titration. So we're going to find the pH of interest for the equivalence point of our weak acid, and then we're going to see what indicator has a reasonable equilibrium close to that.
Okay.
But an indicator changes colors on its own. It doesn't need another weak acid system for it to change colors. You can just put an indicator in water, throw an acid and base, you can change colors.
So with that, are you showing that the disassociation of the weak acid is like affecting the indicator, and that's why it helps? Like the systems are interacting?
Yes, exactly, right? So the systems interact because the indicator's in the beaker with the weak acid. The indicator is typically at a concentration of micromolar, so really low concentration. So the disassociation, the H plus contribution from the indicator is negligible. And it's the weak acid system that's going to dominate the H3O plus. And it's going to essentially push around the indicator based on how much base we add. Okay. I have to answer another question real quick. So everyone pull up midterm one free response problem. Look through it for a moment. Figure out what key questions you have about midterm one free response problem.
If for part B, does it increase the solubility?
Okay, grab this.
She's not trying.
Because I know that it was like, if the anion, they conjugate base for a strong acid.
You're graduating?
Then it'll, I thought it was
Was that enough? Yeah. Okay.
Yeah, that is. Because if you think about it, like, if you wrote down, like, yeah. I forgot that this is so minor. Yeah. Sorry about it. So it would make it more soluble. We made the same mistake.
Are we ready to look at this? Okay. Can I switch that because I don't remember what the problem is. So the problem is we're looking at calcium oxalate. This is a lab question. We're looking at calcium oxalate, and we're looking at some selective solubility. First thing we do is we calculate the KSP value from the given solubility in grams per 100 milliliters. Part B is we write down the reaction of the solubility by considering the calcium oxalate anion. So we write down the two chemical reactions. The first YouTube video I did was exactly this thing. We have calcium oxalate solid interacting with water, put calcium 2+ ions into solution, and oxalate anions into solution. We then decrease the pH, that is to say we add acid, and we say, hey, how would acid potentially interact with this? So I'm going to just add H3O+, and I'm going to look at this, I'm going to say, is H3O+ going to react with calcium 2+? Positive charge interaction, not likely to happen. Is H3O+ going to interact with oxalate? Yeah, that's much more likely. So I'm going to go ahead and see what kind of interesting equilibrium could happen here? I'm going to do the monoprotic interaction. A lot of people jump to the 2-proton interaction. It works, but then you're dealing with 2 equilibria, and we want to do them one at a time. So this is going to go to HC2O4 2 minus, minus aqueous. We're given the Ka. Oh no, we're not given the K. We're asked to write down the Ka expression, product over reactants. We're given the Ka on the next page when we're asked to do the calculation. We're given a Ka. We look at this and we say, okay, the Ka is a small number. It's a number less than 1. That means the equilibrium will lie at least a little bit towards the products, right? It's not going to be all products. It's not going to be all reactants. There's going to be some equilibrium. The fact that this thing forms a little bit, the fact that that forms a little means that this leaves solution. Right, that leaves solution a little bit. If that leaves solution a little bit, then this thing has to redissolve more. Right, to replace the oxalate ions based on the Le Chatelier's principle. As this reacts out of solution, this redissolves more to put the ions back in solution.
What's an instance where the solubility will be like decreased by increasing or decreasing?
Ooh, solubility decreased. Okay, so this is not a question on the midterm, but let's go ahead and look at it real quick. What's a situation where the solubility would be decreased? I can only really think of a few things. What's the name of the effect where we typically see a decrease in solubility?
Yeah, common ion.
Altogether. Common ion effect, that's right. So we're going to look for something where we get a common ion effect. Now, a common ion effect with H3O+, not very likely. One of the only places where I can think of a really good increase in pH, common ion effect, decreases solubility, is if we're looking at something like a calcium hydroxide, which would go to calcium 2+ plus 2OH-. Clearly, in that situation, if we increase the hydroxide concentration by increasing the pH, that would decrease the solubility through the common ion effect. That's the best example I can think of off the top of my head. Right, so any of our hydroxide salts will have their solubility decreased by an increase in pH. Okay, so that's part B. We go on, we look at part C. Part C gives us a starting amount of material. We start with calcium oxalate, we add acid. We ask how much oxalate ends up in solution. The most common mistake was mole ratio and forming all of the oxalic acid, even though I say it's monoprotic. Do we need to see part C? I'm seeing like 2 people not. Okay, let's look at part C. So if we're looking at part C, we've got calcium oxalate plus acid. Right? And we want to look at the clues that are in this problem. We start with this material, we start with that material. How much would end up in solution? So that how much gives us a good stoichiometry clue. in solution gives us a good equilibrium clue. The fact that we're given a Ka gives us a good equilibrium clue. On this problem, I even have a hint. I say hint, do a reaction, and then do an equilibrium. So let's go ahead, let's do a reaction, and let's do an equilibrium. So we're going to assume that these two things react together perfectly and goes all the way towards products. We know that's not exactly true, but we're going to assume it. And then we're going to correct that. So we're going to have our stoichiometry, our reaction, our excess. Our stoichiometry step is going to be 3.94 milligrams times R1 over 128. That's grams per mole. Let me give myself a little bit more space. My H plus is going to be 0.00. Sorry, I gotta read what I'm doing. 0.02 times 3 molar. It's milliliters. I'm going to assume that I've got zeros there. I do 0.394 divided by 128. Well, 3.94. I'm saying the wrong things, but look at the numbers.
0.03.
0.03 what?
Milli.
Oh, I just meant more digits.
Oh, 0.031.
0.031. That's going to be in millimoles because instead of dividing by grams, I divided by milligrams. So that's millimoles. And 0.02 times 3, I think I can do that one in my head. 0.06, also millimoles. Notice in this case, the calcium oxalate is clearly the limiting reactant, doing this in a one reaction step. So I'm going to have minus 0.031, minus 0.031, plus 0.031, plus 0.031. I'm going to get 0. I'm going to get 0.029. Can I do math in my head? 29? Okay. 0.031, 0.031. We then want to say, okay, I've dissolved all of my calcium oxalate. I've got no oxalate left in solution because it all goes to this protonated oxalate form. Ta-da, there's no oxalate in solution. That's not true, right? So then we have to say, okay, the problem was asking how much oxalate ends up in solution. So then I have to say, okay, how much of this thing, right? So having 0 calcium oxalate, having 0 solid left, that's fine. That doesn't affect the equilibrium. But now I want to see how much of this protonated form redisassociates that could then possibly re-react with the calcium. Because like there's a more complicated equilibrium that could be happening. So I'm going to look at my HC2O4 minus plus H2O goes to H3O plus C2O4 2 minus. Aqueous, aqueous, liquid, aqueous. I'm going to start with 0.031 over my total volume, which in this case would be 0.14 plus 0.02, which would be 0.16. I'm starting with 0. Oh, no, I'm not starting with 0 H plus in solution. I've got excess H plus. Don't forget your excess H plus. The excess H plus is essentially going to be a common ion effect here. So I'm going to have 0.029 divided by 0.16. And I'm going to theoretically have 0 oxalate in solution. That's going to be my initial change equilibrium. Minus x plus x plus x. Ka, I wrote down a moment ago, 5.43. Times 10 to the minus 5. Should we use x's small approximation? Yes, always. We always use the excess small approximation. It just might be a bad idea. We're still going to do it. We're going to get this as approximately, what's 0.031 divided by 0.16? Can you help me calculate these concentrations? Will you please?
0.19.
And this one, 0.029 divided by 0.16? 0.18?
Yeah.
So at this point, we can say, okay, I know my equilibrium values. I did the excess small approximation. I'm going to have products over reactants 0.18x divided by 0.19 equals 5.43 times 10 to the minus 5. I'm going to get x is equal to 5.33. Help. I'm just doing math in my head. I don't trust it. Oh, I went the wrong direction. 5.73 times 10 to the minus 5. So now we can look at this and say, okay, there is really not much oxalate left in solution, right? Even though, like, after doing this acid reaction, most of it forms the protonated form. Only a little bit is left in solution that could potentially react with the calcium and make some new precipitate, but not very much. So we look at this and we say, okay, let's do another check real quick. Is the excess small approximation a good idea? I say, let's see. I'm going to check it here. Plus 1, 2, 3, 4. That's 5.73 times 10 to the minus 5. Is the excess small approximation good? 0.18 compared to 0.00005. Excess small approximation looks good. So we can say, great, okay, awesome, that looks fantastic. There's not a lot of oxalate left in solution. Then we go on to part D. And whoa, did you all get part D wrong? The answer that almost everybody gave to part D is if we use a weak acid isn't going to disassociate as much, so it's not going to put as much H plus in solution. So it'll still dissolve the solid, but it won't dissolve the solid as well. Except that's not true. We did this in lab, and we saw the solid, when we added acetic acid, the calcium oxalate didn't dissolve at all. We saw that in the lab. We did this experimentally. No calcium oxalate, well, no visible calcium oxalate dissolved. So how do we explain the fact that a weak acid, even though it's just a weak acid, doesn't dissolve calcium oxalate when a strong acid does? It's more than just the disassociation. Let's look at acetic acid. Oh, I just wrote as oxalic acid again. When acetic acid dissolves in water, it does not just put H plus into solution. It also puts acetate anion into solution. Right? That's really important. Because remember, the entire premise of this equilibrium that we're looking at is the fact that oxalate is in equilibrium, the protonated oxalate is in equilibrium with this. And the protonated oxalate will take, or the deprotonated oxalate will take up the H plus. But if we put a conjugate base into water, could that also react with H plus? Thumbs up for yes, thumbs down for no. Conjugate base reacts with acid. Yeah. It turns out that we create a competition between the conjugate base of oxalate and the conjugate base of acetate, both trying to take up protons. So when we use a weak acid, it doesn't just put the H plus into solution, it also puts the conjugate base into solution. And we run into this problem, particularly with acetic acid. This is part of why we used acetic acid. Can I remember the Ka for acetic acid? 1.7. It turns out that acetic acid gives away its protons worse than oxalic acid. That means this conjugate base is a better base than the oxalate anion. That means any protons that end up in solution are going to react with the oxalate anion rather than are going to react with the acetate anion rather than the oxalate anion. Any protons that end up in solution are going to react with the acetate anion instead of the oxalate ion, which means this equilibrium doesn't happen. This equilibrium goes this way. If you remember back, this was the first lab we did. I can't believe you don't remember this. Remember that first lab we did? Back in like week 2. We did this lab, and we're trying to test the different things. We make calcium oxalate, we make calcium hydrogen phosphate, we make calcium carbonate, right? We made 3 precipitates. And then we said, oh, if we added a strong acid, they all disappear. We can dissolve all of them away. If we add a weak acid, if we add the right weak acid, 2 of them disappear and 1 of them doesn't. The one that didn't disappear was the oxalate, because the oxalic acid is stronger than the acetic acid. But y'all didn't say that on the midterm. I think maybe 2 people said that on the midterm. I gave pretty good partial credit just for explaining like weak acid behavior and stuff like that, but you really had to identify the fact that this weak acid does, so like when we look at a strong acid, you just put H plus into solution. When you look at a weak acid, you put H plus and conjugate base into solution. You have 2 things that can mess with your equilibrium. Question?
Well, with a strong acid, weak base is also
technically, right? So technically, right? So if we look at HCl, you got an H plus Cl minus. Technically, that is a conjugate base, but it's a conjugate base that is worse than water. So it's not going to affect any of the equilibria. Should we look at homework 7 a little bit? Any other questions on this before we move on?
So essentially, since the Ka value for acetic acid is smaller, it's going to want to be more.
Yeah, essentially, since the Ka for acetic acid is smaller, the acetic acid isn't going to disassociate at all, and it's not going to form any oxalic acid. If you don't form any of the monoproduct oxalic acid, you don't affect the equilibrium of the solid at all. Okay. Homework 7. Homework 7 is our molecular orbital theory homework. Do me a favor, take a minute, everyone pull up homework 7. Let's take a look at what kind of questions we got for homework 7.
I was thinking, especially like number 4, why can atoms rotate around a single bond but not around a double bond?
Okay. Yeah.
Also, I'm a little wondering.
Okay, so what questions do we have? What's your first question?
Why can atoms rotate around a single bond but not around double bonds?
So this is going to be pretty hard for me to show. Let me see if I can build something with a model kit real quick. Single bond rotation versus double bond rotation. We can explain why bonds rotate based on the electron clouds. And the model kit does not do a good job of representing this. but it kind of gets the point across. I'm going to try to show it 2 different ways if I have the right parts to do it both ways. But I don't think I... Oh, no, I do. Okay. We'll see how this works. Woo. So when we think about this, we want to think about where the electrons are, how are things aligned, and how would things go out of alignment. So if we think about a single bond, we just have this direct orbital interaction. Rotation happens, doesn't really affect anything, right? Any rotation doesn't affect that bond. Single bonds can rotate. The other way I do it is I just put my fingers like this. You can rotate, right? But if you put a double bond, rotation becomes problematic. If you have a double bond, you got 2 things attached, then it becomes problematic. In terms of what's happening with the orbitals, we've got our direct orbital overlap here, and then we've got our p orbitals above and below that interact. If I rotate away, I break that interaction, which takes energy to happen. In order to break that interaction, the way you rotate a double bond is by breaking it. So that interaction essentially locks the atoms into a particular orientation where they can no longer rotate freely. But if you've just got a single bond, the other interactions are kind of interacting with other things. This can just rotate freely. In the model kit, the way it's built, you can see single bond, I can rotate. Let's attach things so you can actually see the bond rotating. Right? I can have these things aligned, or I could have them opposite, or I could have them kind of any rotational orientation, no effect. If I go to a double bond, and the model kits are built to kind of make it so you can't rotate, but you notice that double bond no longer rotates. The rationale behind that is the orbital interaction, the way that these unhybridized, or the way that these molecular orbitals interact with each other, where in order to rotate, I would have to ruin the orientation and essentially destroy the bond. This is going to, again, I mentioned using NMR and the benzene ring, I think, on Friday. This bond rotation idea is also going to become very important in NMR when you get to it, or when you take organic chemistry. Because essentially, if you have a rotating bond, all things attached essentially spin average, and you get 1 peak. But if you have a bond that can't rotate, you get unique peaks for each thing attached.
Okay, so like that piece right there, since you have one, is it a sigma bond, like the green piece to the...
No, yeah, so there's a sigma bond here between the carbon and the chlorine, and that bond could rotate, but this double-double bond between the 2 carbons cannot rotate.
Okay, and can you maybe do like a small clarification again on like sigma bonds and pi bonds?
So sigma bonds and pi bonds are kind of definitional. Sigma bonds are direct overlaps. When we were doing hybrid orbital theory, the hybrid orbitals that directly interacted with each other were sigma bonds. Pi bonds are indirect interaction. So if we go back to this example, the sigma bond in this atom is from an orbital on this purple one with an orbital on this silver one directly interacting, like they're actually overlapping and touching each other. The pi bond happens just from these orbitals on top and these orbitals on bottom being in close proximity to each other. Not necessarily directly overlapping, just being close enough to each other that they can interact. And that's a pi bond. They give rise to some pretty interesting physical properties when you start looking at larger molecules, like the thing I mentioned in benzene, where if you have pi orbitals along the entire top, you can actually get ring currents. You can get electrons kind of freely flowing around the top of a conjugated pi system.
Oh, was it just p orbital? So p orbitals is where the interaction.
Yeah, and we have to be careful about this, right? Because once we start to change the way we define atomic orbitals versus molecular orbitals, it really gets a little bit more cloudy, because d orbitals can also have pi interactions, right? And so when you go to your molecular orbital theory, it's anything that's indirectly interacting is a pi interaction. And other homework 7 questions? Yeah.
So you'd say the pi bonds result from overlapping hybridized orbitals? Or it doesn't have to be?
It doesn't have to be hybrid orbitals. It doesn't have to be unhybridized orbitals, because the definition of pi bonds is good for hybrid orbital theory. It's also good for molecular orbital theory, right? It works for both. Hybrid orbitals really borrowed that sigma pi from molecular orbital theory, where in molecular orbital theory, we don't talk about hybridized or unhybridized, because we're not doing that. We're creating molecular orbitals. A little different. Is that okay?
Well, I just related to question 8.
What's question 8 say?
Yeah, it says, in a typical multiple bond, the sigma bond results from overlap of blank orbitals, and the pi bonds result from overlap of blank orbitals.
Ooh, I don't like the wording in that problem. But so that is a problem that I probably took from a 127 homework assignment that was specifically talking about hybrid orbital theory, not molecular orbital theory, which is why I don't like the wording of that problem once we start doing molecular orbital theory. So in hybrid orbital theory, we can talk about the direct interaction of the hybridized orbitals versus the indirect interaction of the unhybridized orbitals. But once you go to molecular orbital theory, you stop talking about hybrids. You talk about molecular orbitals. Question?
So I just wanted to confirm half-life questions and equals mc squared.
Half-life questions won't be on the midterm, and the equals mc squared questions will not be on the midterm. I'm sad about it, but I told you it wouldn't be, so it won't be. Yeah.
So for molecular orbital theory, I know we have like the sigma, the pi, and then like sigma and pi star.
Mm-hmm.
Like what kind of questions could be asked about those? I'm just sort of confused, like how this all ties together, because we did the molecular orbital diagrams and then we showed like where the electrons are filled in and stuff, but I'm just sort of confused how that relates to like the overall structure of what it would look like, I guess. I don't know, because you gave us those problems where it was like, look at this molecule and say how many sigma and pi bonds and stuff.
Oh, I see what you're saying. So the warm-up problems I gave you, which were kind of 127 review, where I gave you something that was like, I gave you some picture that was like this, and I said, tell me how many sigma bonds there are, tell me how many pi bonds there are, and you want to know how this relates to molecular orbital theory. Yeah, so this is part of why organic chemistry loves hybrid orbital theory and not molecular orbital theory. Because in order to describe this molecule for molecular orbital theory, you would have to solve a system of equations where you have a number of equations equal to the number of valence electrons in the molecule. Right? So each carbon has 4 valence electrons, each oxygen has 6, and each hydrogen has 1. That is a C7O2H6. So that's 6 and 30 and 40. Oh, wait. And 28 electrons from the carbons, 12 electrons from that. So that's going to be 30, 40, 46, a system of 46 variables. Well, 46 times 3 variables. You have to solve a system of equations that has essentially 46 equations in it. And It's like, oh, that's a lot. It is. Computer programs we have today can actually solve that relatively quickly, and we could actually pull up the MOLDI program. That's actually what it's called. It's molecular dynamics, and we could do some calculations, and it spits out the answers for these in a few minutes. It does the calculations pretty quick, but if you just want to glance at it and be able to talk about the sigmas and the pi's and the geometry, hybrid orbital theory does great, right? We don't need to go to all the way to molecular orbital theory to do this. However, if you wanted to get the magnetic well, you probably even do the magnetic properties with just hybrid orbital theory. But if you wanted to get the optical properties, if you wanted to get the energy levels, then you'd have to do the molecular orbital theory calculations. So for these larger molecules, I begrudgingly admit that hybrid orbital theory is a lot easier and gets us enough information.
Okay, so for molecular orbital theory, like all we really would need to know is how to do the diagrams and then how to do the bond order and what the bond order means and like the HOMO and LUMO and stuff.
Yeah, so for molecular orbital theory, we pretty much restricted ourselves to the diatomic cases. We did get to the heteronuclear and the homonuclear diatomic cases, but we just restricted ourselves to the diatomic cases. So I want to do frost circles right now, but I also don't want to confuse you. Diatomic cases. Diatomic cases. Yeah.
So does that mean that the CO and the NO on the bottom will not be on the test?
Those are diatomics.
How would you combine those?
What do you mean?
Also, like, what would the arrangement of the orbitals be on those?
Ooh. So if we wanted to know the arrangement, carbon monoxide. Is that well? Let's do nitrogen monoxide. Right? Was it NO was one of the choices?
Yeah.
Nitrogen monoxide. Is this going to be a high electronegativity or low electronegativity case?
High.
Pretty high, right? Oxygen is high electronegativity. Nitrogen is pretty close to it. We're definitely going to do the high electronegativity case. Here's our p orbitals. Here's our s orbital. We're going to fill in the number of electrons from that. Right? The fact that it's something as higher electronegativity, the weird thing that's going to happen is the p orbitals on the oxygen are going to be higher energy than the p orbitals on the nitrogen. So we're going to get this uneven splitting, but the molecular orbital is still going to end up pretty much the same. Yeah.
In the homework it said to use the nitrogen MO energy splitting, so I thought it would be the
For nitrogen monoxide or for carbon monoxide?
SSCO and NO.
Oh, for both of them.
Yeah. Like, will you tell us on the?
Yeah, I would argue that the nitrogen monoxide should probably use the oxygen, the oxygen form. The carbon monoxide, I'm not sure. The carbon monoxide. So if we looked at the carbon monoxide case, so the homework tells you which pattern to use, which is nice. If we looked at carbon monoxide, you could say, okay, high electronegativity, low electronegativity, which pattern are we going to get from this? So that could be tricky. Now, the homework says you're just going to use the nitrogen pattern for this case. You could make an energetic argument for essentially, right, these three levels getting really close to each other and it being hard to tell which one's above and which one's below. And I would never expect you to figure that out on your own. I would always tell you that, right? So homework tells you which pattern to use, and then you just fill in the electrons. So yeah, those are the still diatomics. I'm thinking back to matrix mathematics now. I haven't done it in a while. Question?
I think there's one homework.
Okay, are we good with homework 7? Was that good? Any other questions on homework 7? Yeah.
So when it has like a 2 minus combination, should we just subtract? No, I'm sorry, 2 plus. Should we subtract an electron from each side? Or just
Yeah, that's fine.
Okay.
So if you have a situation where you're looking at a 2+, you can take an electron away from each side. The most important thing is just make sure you remove 2 electrons from the molecule. And if you're doing a 2-, you could add 1 electron to each side, but the important thing is to add 2 electrons to the molecule. Question?
When you said sketch the highest occupied molecular orbital for 11, do you mean just drawing this thing?
Yeah, draw the picture. Yeah. And I don't know if I have any picture drawing problems on the midterm, just because I don't want to, or sorry, on the exam, because drawing's hard. My pictures don't look pretty. It feels bad. It feels wrong to grade people based on their picture drawing. Question here and there.
This is on homework 7 still, sorry. We were drawing the molecular orbital diagrams, and it said to find the HOMO-LUMO gap on F, but like all of the, there was no unoccupied.
So you have to keep in mind, I know which one you're talking about. So you're looking at the fluorine case, and you're looking at like the F- case.
I was looking at the N case.
Any case.
The neon.
Oh, looking at neon. Okay, so you're doing neon plus, you're looking at the HOMO-LUMO gap. So let's go ahead and look at that. We're looking at neon. Looking at neon. So you're looking at diatomic neon, which is pretty weird. Doesn't really work. And you've got your sigma 1s, your sigma 1s star. And you're saying, where's my LUMO? Can you go to the 2s? We didn't draw it, but it still exists up here, right? So that's actually going to be where your gap is. In this case, you're going to have your HOMO-LUMO gap. Your highest occupied is going to be the sigma 1s star. Your lowest unoccupied is going to be all the way up here at the sigma 2p. Don't forget that just because we don't draw the orbitals doesn't mean they don't exist up there.
But doesn't neon already have 2p? Yeah.
Oh, sorry, I did helium instead of neon. Okay, I did helium here.
That works too, but it's kind of...
Same idea, right? It's just the orbital that's next up.
Okay.
If we're doing neon, let's go ahead and look at neon. How many valence electrons does neon have? Where is neon in the periodic table? Okay, so it's going to be the 2s, 2p, 2p, 2s. This one's full. I think I glanced at your homework and saw something that wasn't what I was supposed to be looking at. We'll do this pattern. We're going to have this pretty much all the way full. 1 electron unoccupied there. This would be the sigma 2p star. So the next energy level up would be the sigma 3s. Same idea, right? It's just, we didn't draw it, but there's still orbitals up there. Other homework 7 questions there in the neck. Yeah.
A question about the diatomic neon example. We're using the high electronegativity pattern, the low.
Yeah, this is where it's more the high electron affinity, right? So I've been calling it electronegativity because when bonds are interesting, it's electronegativity. But anything that's going to pull the electrons towards it a lot is going to have this orientation. So neon also ends up with this orientation, but neon doesn't really do this, right? It doesn't bond.
Right. Okay. So you said it pulls.
Right. So it's the number of protons in the middle pulling the electrons in for the outer shell. That's what gives it this orientation. Other homework 7 questions? If I remember correctly, there was, I'm hoping we can wrap, oh my goodness, it's later than I thought. I'm hoping we can wrap up pretty soon, but I saw there was another question. It was, someone said they wanted a different homework
I have a
question.
quick question.
Yeah. Homework 8, yes, yes.
So there was a problem, like within type 5, that was asking about gamma. I think it just said like gamma radiation or emission or something. And then also, when it says something undergoes electron capture versus electron capture by an element.
Those are also, this is vernacular terms, right? So whether it's undergoing electron capture or it's, going through the process of electron capture, or if electron capture happens to it, those all mean the same thing, right? The process of nuclear decay is electron capture. And then the other one was gamma emission.
I was asking about that somewhere. I can't find it.
That was something we mentioned briefly. So essentially, anytime we go through a nuclear decay, you produce an excited nuclear state, and you almost always have gamma emission as well during your nuclear decay. It's not as interesting to us in terms of the chemical composition change, but physicists care a lot about that because you have to account for all the energy somehow. Wow, I meant to stop a half hour ago, but I'm going to go ahead. I'm going to stop the video. I'm going to wrap things up, but I'll stick around and keep answering questions if you still have questions. Sound good? Okay, great. I'll see you all on Monday.